then I think it's already 5 past. We can start slowly. So good afternoon, everyone. We're really happy to host you here to our joint online stakeholder workshop between the MOST-H2 project and MAST3RBOOST project. My name is Sophie von Strahlendorf. I work at Steinbachs Europazentrum, and I'm the Communication Dissemination Project Manager for MOST-H2. I organized this, or we, together with Estibaliz Gamendia from MAST3RBOOST, who is also the Communication Dissemination Manager there. So this is really a joint initiative. And we're really happy that you took the time today, even in the hot summertime, just before the holidays, to still join us, because both our projects are in the final phase now. And we really wanted to do this one joint stakeholder dialogue at the very end to really have a good dialogue between our projects, but also, which is most important, with the audience. So we're really happy to have you here to also be actively involved. Today's session is called From Innovation to Uptake. So as said, we really want to tackle the question how innovative hydrogen storage technologies can move from the lab, from innovative project results to really real-world application and the market. So yeah, we really aim to have a nice dialogue with you. Both projects are working on adsorption-based hydrogen storage technologies. So we would really like to use today's exchange to better understand this topic of hydrogen technologies. And it's really, as already said, intended as an interactive exchange. We will first present key developments from both projects. So we have speakers, experts from both projects here who will briefly present what has been done and what are maybe also our questions to you. And then later on, the second half is really dedicated to the dialogue. So we will have a Mentimeter and invite you to actively participate. You can do this if you want to open your microphone. This is possible, but you can also just write into the chat so that we can read the questions. Just as last information, we will also register and record the meeting. So just if you don't want to appear here, you can just leave your camera off, but we would also be happy to see your faces to have this dialogue, really to have it together. Yeah, and I think we can already move to the next slide, Estibaliz. Thank you. This is just a short overview so that you can see who is here. So as said, we have these both of these projects, MOST-H2 and MAST3RBOOST. We are sister projects, so we are from the same call, funded, and we both started in 2022 and end this year. So as said, we are already in our final phase. This slide just shows the common ground. I will not go through each different bullet point, but you can have a look. We work both on adsorption-based hydrogen storage, as already said, but from complementary angles. Materials development, system integration, future application pathways is both of our target here. And this shared joint workshop today is really focusing on the question, what is needed to move adsorption-based H2 storage from promising project results towards real-world application. So this is why we're here. On the next slide, we see the agenda that I would like to briefly walk you through before we start. So we have 1.5 hours time. We will start with a keynote input, which is a recording from Jorge Chatzimarkakis. This is the CEO of Hydrogen Europe. Unfortunately, he couldn't join us today, but he did a recording of himself and sent us the video, which is very kind of him. Afterwards, we will have 2 project presentations by MOST-H2 and MAST3RBOOST with our coordinator for MOST-H2, which is Theodoros Steriotis, and both representatives on MAST3RBOOST, which is Paolo Tadei Padei and Teresa Valdez Solis. And afterwards, as said, the second half will be dedicated to the real discussion with you. And at the very end, we will also have a consolidation of the key takeaways and future needs, which will be guided by the 2 project representatives. But of course, also here you can also join. Yeah, and with that, I think it's already time right now, yeah, 10 minutes after, to start with a keynote input. So I would invite Estibaliz if you can share the video. It's a 5-minute video by Jorge Chatzimarkakis from CEO from Hydrogen Europe, where we could have a brief intro.
Hello, Miss Maddie.
It takes a while to change the screen.
Sorry, just having some troubles here. Let me check again. Okay.
No, it works.
Can you see the screen, right?
I can see it. I think everyone else as well. Maybe we just check with the sound.
Yeah, let me check the sound first. Again, sorry. Okay, there it is. Okay. Nice. Okay.
Good morning, everybody.
Thank you.
Welcome to this important seminar workshop of MOST-H2 and the MAST3RBOOST European research projects. You are at a very important point of European development on technology, on industry. Why is this? We have seen the last 10 years, the last decade, a fantastic development of hydrogen technologies, which was a niche into a market-oriented, bigger technology orientation. A family, a sector has been born over these 10 years, and it was under the guidance of the Paris Agreement of climate change, of stopping climate change and enabling with hydrogen exactly these developments. However, now we are at a new tipping point. Europe has understood that the geopolitical turmoil and the idea of bandwagoning on cheap energy that we just import as Europeans all over these years is not to be continued. This is why we need to self-source our energy, our molecules, in order to be less vulnerable. We call this resilience, and this is exactly why the hydrogen technologies, and you are at the ground, at the fundament of this development, need to be developed also to gain new sovereignty. We can produce renewable energies, but we have difficulties at the moment to manage them, to create flexibility in the power grids. And this is the place where hydrogen exactly can smoothen the stress for the grid, but at the same time use the energy produced in car applications, so mobility, in trains, in planes, with derivatives of hydrogen, of course also in shipping. And you are in Greece. Greece is a big shipping nation. So all these developments together put upon us a responsibility to further research, to further innovate, and to continue the path, maybe with another angle or with an additional angle, but that just makes us, the hydrogen sector, more important. We'll see what you do there in your workshop, and I wish you success. I wish you good talks. I wish you good ideas, and I wish you creativity to continue this journey.
Okay, thank you very much. So many thanks to having organized this, Theodore, because you had the contact to Hydrogen Europe. So I think we have a good set of the scene now. And I would like to come back to the speaker slide because this is something we still need to see before we start. So after the agenda, I think we have one more slide presenting the speakers, right? So we will, as I already said, we will have our MOST-H2 coordinator, Theodoros Deriotis, who is the research director at the National Center for Scientific Research Democritus in Athens, and two speakers from MAST3RBOOST, Paolo Tadei-Padei, managing director of Spike Renewables, and Teresa Valdez Iglesias. I hope I pronounce it correctly. I'm sorry if not. Tenured scientist at the Institute of Carbon Science and Technology at CISIC. And I think, Theodore, you will start with the MOST-H2 presentation. We will have now half an hour, so 15 minutes per project, to just briefly introduce you to the project, what has been done, what is our more or less a general set, and then afterwards we can start into the discussion. So I would like to give the floor now to Theodore, and the slides should be integrated here, so you can just say next slide if you would like to change. Thank you.
Thank you. Thank you very much, Sophie. Thank you, Estebalis, for organizing this meeting today. So I will start with a typical picture. Will not dwell that much here. We all know about hydrogen economy is of the future. Is a molecule that can play a pivotal role in the energy landscape. It can be combined with renewables or traditional sources. It can be used as an energy token or as a fuel itself. And this has been recognized for the past perhaps 10, 15 years by European Commission, and there are several activities around hydrogen, like the Green Deal, the Fit for 5. There is a strategy, a roadmap for deploying hydrogen technologies, and also the REPower EU is a complementary action in the European level. Now, hydrogen economy is based on this box, the square of hydrogen, as they say. There are 4 corners: production, storage, utilization, and safety. We will be talking about storage only today. So if we can move to the next slide. I will try, if you can bear with me for a couple of minutes, to explain as simply as possible the challenges in hydrogen storage. So perhaps you all remember from your high school years the 3 states of matter: solid, liquid, and gas. Their difference is actually density, or else, in simple words, how efficiently the molecules or the atoms are packed together, how close they are together. And this is based on the yin and yang of physics, which is the interplay between the kinetic energy and the intermolecular forces. The kinetic energy increases with temperature, and the intermolecular forces increase, let's say, with more atomic or molecular weight and the polarity. We are very unlucky in this case, because hydrogen is the lightest molecule in the universe, and it's non-polar. So it makes up a very, very thin gas that can escape the gravity of Earth, actually. Hydrogen and helium can only do this. So the conventional storage technologies are based on playing with this interplay between kinetic energy and molecular forces. So one way to store hydrogen is to decrease the temperature, so immobilize the molecules as much as possible. So we turn hydrogen into a liquid, but this happens in a very, very low temperature, minus 253 Celsius or 20 K. And there we get a good density for hydrogen. It's the density of a liquid phase. Another way is to try to apply pressure and squeeze the molecules together at normal temperature. But then we should apply enormous pressures, like 700 bar for the tank, or 1,000 bar for the refueling station. And there we get only medium, let's say, densities. There are some chemical routes to store hydrogen, but both projects are based on cryo-adsorption, which is an alternative physical method. It resembles a little bit like the condensation of humidity in the windows in a cold winter day. So we do a trick here. We use these large molecules that you see, these surfaces or these tubes. They are actually a method to increase the interaction between hydrogen and the second molecule. So because we increase the interaction, hydrogen molecules tend to stick on the surface, and then we increase the density of hydrogen. Or else we can squeeze hydrogen molecules inside these tiny tubes as shown in the right. This happens in milder conditions, so at almost minus 200 Celsius and much lower pressure, 100 bar, and can reach very high densities, even higher than the liquid. Can we move to the other slide, please? Now, we use porous materials for this case, and on the upper left, right, you see exactly the reason why we do this. If we take a solid, let's say, and we start drilling pores in this, we are increasing the efficiency by both ways. we increase the surface area, and because we said that it's a surface interaction, we increase the interaction, the extent of interaction with the hydrogen molecules, and then we decrease the weight. So we use more surface and less material. And this is exactly what is happening with activated carbons. You will hear about this in the next presentation. Another way to make pores in a material is an additive way, which was discovered perhaps 25, maybe 30 years ago, and led to the Nobel Prize in Chemistry last year. And it's the metal organic frameworks. There you take simple organic linkers, very light, and metal connectors, which can be ions or clusters. And then you build up chemically a framework which is empty by construction. It looks like the pictures on the right, and one can reach extremely high surfaces, over 7,000 square meters per gram. And most importantly, one can tune the pore sizes by, for instance, choosing the length of the linker. Next slide, please. Now, adsorption is a well-known technology. It has been used by over a century. So it's a mature technology, and if we get the right material, it will be quite easy to deploy this technology for hydrogen storage. It's mainly used for separations. Again, it's always connected with the large surface area and the nano confinement, putting things in very tiny spaces in pores. And for the case of nitrogen, it has been discovered that there is even a more or less linear relationship between the gravimetric capacity of a material and the specific surface area of the material. Next slide. So in MOST-H2, what we try to do, we start from the very fundamental level in the lab by using artificial intelligence coupled with chemical knowledge. We build new materials, new MOFs, by combining different linkers and metal clusters. We characterize them, and the most successful were upscaled and formulated as monolithic materials, which can be used in practical applications. And finally, we have designed and built a tank that can allow for cryogenic adsorption cycles, and this tank is filled with the best performing of our material. Now we use all these to study one more or less application, an umbrella of application, which is heavy duty transport, i.e. trains, buses, and trucks. Next slide. Where we are now. We were extremely lucky. We have discovered at least 2 or 3 materials which are have the best balance in amongst all MOFs, the best balanced gravimetric and volumetric capacity. You can see our results in this comparison with of the deliverable capacities with the top performing materials in the literature. The best and most stable of these materials was formulated as monolithic, and then the synthesis was upscaled. Currently, the scale is 1 kilo per day. We have already 6.5, close to 7 kilograms available. The material is quite stable. We have cycled it over 2,000, close to 2,050 times at 100 about 77K. Can be extruded, and the extrude dates are really robust. They outperform the zeolite extrude dates. Next slide. On the other hand, to 20-liter tank, 18 to be exact, has been developed. You can see the picture on the left. It is now traveling from Spain, from La Pesa to Athens, where it will be installed in our research refueling station, where we will run the final demonstration of the project. This is planned for mid-September. You can see the design of this reactor on the right, and we have also used tools to simulate the whole process inside this reactor. Next slide. Now, the main application, as I mentioned before, is heavy-duty transportation. We have been relying on a project that is in Austria, in the Tyrol area. It's a small train line. They call it narrow gauge, the Zillertal band, in the ski area, let's say, the Tyrol area. It operates at 32 kilometers, and the loading is 320 kilograms of hydrogen. The refilling is daily, and as mentioned before, the conditions are 100 bar 77 K. The refilling time should be below 30 minutes. In parallel, we have been extending this study in Italy. The Italian case is another much longer non-electrifiable line, where we also have been studying the infrastructure that supports a hydrogen train operating in this area. That means the refueling stations that should be available. Next slide. So far, what we have seen that there are certain advantages in the technology that we are proposing compared to both traditional technologies like compressed gas and liquid hydrogen. So safety is the first issue. We use 100 bar instead of 350 or 700 bar for the compressed gas, and at this case, the boil off that happens at liquid hydrogen temperatures at 20 K is significantly lower. The tank price is, of course, a major advantage because it's much lower because of the lower pressure or the higher temperature than both cases. And we gain money, we gain cost from the compression to 100 bar instead of 300 bar, or the cooling energy that we need. And this is on a daily or on a refilling basis. I mean, every time we fill the tank, we gain a lot of energy. On the other hand, we have the cost of the material, which is not significant, but highly depends, the final outcome always depends on the cycling capabilities of the materials in the terms of thousands of cycles. And the economy of scale, how cheap one can make the material in ton quantities. Next slide, and thank you for your attention. This is the consortium in a very happy moment in Alicante, Spain. Thank you very much.
Thank you very much, Teodoro. Yes, I remember that. That was a nice meeting in Alicante at one of our partners. So thank you for this comprehensive overview of the general methodology of hydrogen storage, but also MOST-H2, where we are now, how the project connects material development, tank integration, and application-oriented testing, and what has been achieved. We would now move, I think, before we start with questions. So if you have any questions, you can already type them in the chat if you don't want to forget. But I think we will just move on because we are perfectly on time with the next presentation, MAST3RBOOST. This will complement the MOST-H2 presentation by focusing strongly on how adsorption materials can be translated into an integrated application-oriented hydrogen storage system. So I'm pleased to hand over to our two speakers from MAST3RBOOST. I don't know who wants to start, Teresa or Paolo.
I'm going to start.
Okay, perfect. Then the floor is yours. Thank you.
So thank you. As you are going to see in the next minutes, MAST3RBOOST and MOST-H2 shares a wide area of interest. We are working in the same scale of temperatures and pressures. We are working with similar materials in some cases, but well, there are also small differences between the two projects. We are targeting a 1 kilogram hydrogen demonstrator that will be filled with MOFs, as in the case of MOST-H2, but also with carbon materials. And in this project that we are almost finishing as well, there are a wide interest in the developing and testing of these materials from lab scale to higher volume and mass scale. Next slide, please, Steve. Theodore said that one of the problems or the disadvantages of MOST-H2 approach is the cost of MOF materials. We have the same problem with any of the projects that we are starting or working on, and we have trying to focus on the use of residues from starting points, from precursors, from this kind of materials in the case of activated carbon, but also in the case of MOFs, as our colleagues of South Africa does. In the case of carbon materials, we are using residual biomass as a feedstock for carbon materials, basically from pistachio shells, sawdust, and also some materials such as liquid stones. But we are also working on a synthetic approach using green polymers and microwave treatments for the synthesis of very specific compounds that can be produced carbon materials with very concrete properties, very specific properties. We have performed in every case LCA analysis to see which are the key points from the strategical, economical, and environmental point of view. And we have also tested the scale-up feasibility of these materials. In the case of MOFs materials, we have been used PET-derived materials as linker, and they are also using some residues from mining waters in the case of iron, and multi-layer packages in the case of aluminum, just to keep in mind this idea of decrease the cost of precursors and trying to produce materials in a renewable and sustainable point of view. Next slide, please, Steve. Okay. Well, the key point in the synthesis of porous materials, of porous activated carbon, are depicted here. We are starting from that biomass that I told you a few moments ago, and we have two key steps that are the hydrothermal carbonization and the CO2 activation. In these cases, we are controlling the porosity just to be sure that we have materials with very specific properties, having a really special control of the porosity, the size of the pores, the amount of pores that we have. What we are doing, in fact, is just to burn the amount of carbon that we don't need to put the hydrogen in that holes, in that specific holes. We have tried very different approaches, but we know that it is very difficult to upscale this process into an industrial scale, because we are using very long activation times that are useful to control very well the properties of the final carbon, but this is not useful for the real application. So next slide, please. We have been using here is depicted for the case of green polymers, but it's the same approach in the case of biomass. We have been using chemical activation as well. In this case of chemical activation, we mix a chemical product that is potassium hydroxide with the precursor of a precarbonized precursor to reduce the time, to reduce the energetic need of the process to have the final activated carbon. In this case, what we are using as green polymers are materials such as glucose, tannin, citric acid, very simple materials that can be treated to produce a very tiny microsphere of homogeneous size, depending on the condition that we use from the synthesis, and having a final similar distribution or a similar shape in the activated carbon. That is also good for the packaging of the final material at the end of the process. Next slide, please, Estíbaliz. Well, these are our last results. If you remember the best carbon material that Fyodor showed you a few moments ago, it was much below our materials. We are around 11% in some materials, 11% of hydrogen uptake of at 100 bars, not for carbon materials, but for other materials with ionic liquids that are not useful for the scale up of these materials. But we are having quite good behavior with carbon materials as well. Next slide, please. And well, we have here a couple of slides showing how we are dealing with the scaling up of these materials. We have been trying with CO2 activation, as you see here, but we have very small amounts of carbon at the end. So we have moved to the chemical activation process. Next slide, please. And next slide, please, Estíbaliz. And in this case, we can have a really high amount of precursor in each batch. So we have been doing, as our colleagues of MOST-H2, a pelletizing process having around 1 kilogram per hour, and we have produced this 8 kilograms of four different materials, 2 from carbon materials and another 2 of MOFs, to fill our 22 liters tank and to test them in realistic conditions. I'm not sure if this is my last slide or not. Yeah, so I give the micro to Paolo to keep on the explaining of the MAST3RBOOST project.
Okay, thank you, Teresa and Theodore. Okay, yes, I'm Paolo Taddei from Spike. We were involved in the MAST3RBOOST project, mainly on the simulation and design of the tank and filling system. So here we would start from the simulation, and we use multiphysics software. COMSOL multiphysics. In this case, we made a simulation based on different parameters to simulate the absorption of activated carbons and MOF. The important thing is the first step that we did validation against experimental data from a 2.5 liter that was in literature present as an experiment performed in Canada some years ago. And so we validate the simulation before with this real data, and then move to another geometry, to our geometry, and of course to the specification and characteristic of different activated carbons and molten organic frameworks. So what is important from the simulation point of view is that we can let's say, change in a computer the temperature, the inlet temperature. We can modify a lot of parameters and see which is the best suited temperature and pressure and ramp rate and all the parameters that's best suited for the specific geometry and the specific material that act as an absorbent. So the next slide shows the digital twin. That is an application that I think is very useful for design, because we can modify the geometry, we can modify all the parameters of the activated carbons. We have a lot of different specifications from many different samples. And we can also modify the inlet temperature, so we can cool down the hydrogen before the inlet, or we cannot and see the difference. We may modify the input inside the tank and see where the hot spots are, and we want to avoid hot spots. Of course, it's quite easy to imagine that every time that we have a high absorption, we have high temperature. So in our case, all this instrument was used also for the dimensioning of the heat exchanger. So what we did was a tank. We will see in the next slide, I think, the geometry. Yes. This is the outlet, of course, of the tank, but you can see a flange. If we keep out the flange, we will see a cylinder. And inside the cylinder, we have a heat exchanger that is the main purpose is, of course, to cool down the tank during the filling, because you have to imagine that every time I put some hydrogen, I generate some heat. So we really need to keep the temperature as much as possible near to the operational temperature, that is 70 K. During all the process to reach from 3 bar to 100 bar. So the heat exchanger is fed by liquid nitrogen, because nitrogen vaporizes at 77 Kelvin. So it's very good to have this kind of cooling system. But of course, you have a system that need to handle also the nitrogen together with hydrogen. So the system around this tank is quite complex. I think in the next slide we have a simplified P&ID. Yeah, this is a simplified because of course the real P&ID is more complex. And what we see here is that we have an insulation made by a vacuum pump, because the cylinder you have seen before has an inner cylinder with vacuum, because vacuum is the best insulation method. We want to keep 70 K, probably inside a car or inside a train where the temperature outside is much higher. Then we have two lines. You see in blue is the liquid nitrogen. Liquid nitrogen feed the tank itself, the heat exchanger inside the tank itself, but also an heat exchanger that is outside. So the purpose is here to cool down the hydrogen before the inlet. And what we see from the simulation is that the absorption is faster, and we reduce hot spots, and the final absorption is improved by the cooling of the hydrogen before the injection. We have also a green line of gaseous nitrogen, because we want to degas the activated carbons. So inside the same heat exchanger, we put sometimes some high temperature nitrogen to degas the inside of the content, let's say, of the tank, to degas the activated carbons, to get rid of oxygen and other gases. So to be sure that when we fill in with hydrogen, we have only nitrogen and nothing else. So all this system is quite complex, and if you can imagine that when we are talking about commercial solution, we have to bring all this system inside a mobile device, so whatever it is. The other point is quite important is that we made all these tank with a special construction method that was wire arc additive manufacturing. So this was made in aluminum because aluminum is one of the few, let's say, metals that are suitable for this kind of technology. And this is an innovation, I would say, inside the innovation of the hydrogen storage, because there are no standards at the moment that we can rely on for the qualification and certification of the tank. And so we perform a FEM analysis, another numerical simulation, but based on a stress to evaluate the von Mises stress in every point. At the end, we design it, and the first test we perform, we wanted to reach, of course, 100 bar as operational pressure, and the tank was suitable for reaching up to 300 bar. So the design was, I would say, sufficiently safe, even if not sufficient from the point of view of certification. So for the final certification, we are in the moment under a full test program that include a bar test and some also leak test. Another point that seems easy, but was not at all easy to find some bolts suitable for this application, because we wanted to have bolt on aluminum because we want to have the same kind of material for flange, tank, whatever, because the thermal expansion must be the same. Otherwise, when you change temperature, the differences in length because of thermal expansion may cause some leakage. And so it was not easy to find the bolts, but at the end we managed also to find this solution. So these are all the activity related for the design and the simulation of our system that is under testing in this period. I think this is the last one from my side.
Okay.
Thank you for attention.
Thank you very much, Paolo and Teresa. That was very interesting also to see what MAST3RBOOST was working on or is still working on, and more technical explanations from your side. So thank you also for staying in the time. It's also always important for us, for the organizational team. So thanks for that. I think we can then now move into the more active part after we heard from both projects. We have here a Mentimeter, and the main objective, as already said, of this section is now to collect your perspectives on what is needed to bring adsorption-based hydrogen storage solutions closer to real application. I hope the code works for everyone, so you can start logging in. But of course, you can also, if you want to directly react, you can also use your microphone for that, or just use the chat. Just keep in mind, you do not need to be a technical expert in every aspect of hydrogen storage to contribute. We are interested really in different perspectives. So from research, industry mobility, infrastructure policy, everyone who can has an idea is really invited to participate here. And yeah, I think with that, I will just keep just some more time so that everyone can log in. And then I think, Estebalis, we can also go slowly to the first question. So let us start with this question. It's a open warm-up question. So in one word, what comes to your mind when you think about adsorption-based hydrogen storage? So you can just think what could be something that comes to your mind. I mean, it can be anything. I see already something appear: alternative, hydrides, adsorption, energy, safety, expensive, research, alternative already twice, yes. Low temperature also. Complex. So this is very useful for us because it really shows how different the topic can be approached from different sides, from materials, storage performance to, yeah, safety, scalability, mobility. Yeah, requirements, innovation. So nearly everyone has responded. Okay, so we can, I think, yes, go to the second question. So which technological aspect should be the highest priority for future development? So this could relate, for example, you have different options here to materials, storage capacity, tank design, thermal management, refueling, safety, scalability, system integration, or validation under realistic conditions. So this is really, you can tick here what you think. Yeah, so most people at the moment say manufacturing scalability and reducing operating temperature requirements, but also long-term material durability, okay? Give you a bit more time. Yes, Teresa, you already commented. If you want, you can also open your mic. That was in the chat. Thank you for that. So the question was for both presentations, which were the performances achieved as hydrogen reservoir? And Teresa responded that they have achieved good cyclability, but that the tests are still lab scale tests, so they still need the realistic test. Oh, you're already at the next question. Okay, sorry. So the next question, I'm a bit slow, is which barriers currently limit the uptake of adsorption-based hydrogen storage the most? So it's about the barriers. This could include the technological barriers, of course, the high system costs, which are the most people voted for, I see. Yeah. We already heard it in the presentations also beforehand that the costs are really something that is really critical.
Yeah, but that high system cost is what we are trying to deal with, at least with the materials synthesis, no? So yes. We are maybe, well, at least we have identified the original.
At least you have identified the right barriers.
Yeah.
So it's good, yeah. We try to find the solution to the barriers, yeah.
Yeah.
Yeah, so this system cost is really the winner of this, but we also have limited demonstration projects, yes, regulatory uncertainty and lack of standards. So regulatory uncertainty, sometimes regulations can help, but sometimes they can also hinder. So it's always difficult. But yes, lack of hydrogen infrastructure, of course. Yeah. Okay, next question. We're really fast here. So now we go to the more positive side. So which sectors do you see as the most promising for adsorption-based hydrogen storage? So you may think about rail, maritime, heavy-duty transport, hydrogen infrastructure, industrial applications, stationary storage, or other use cases. So just what do you think? Which sectors are the most promising? So I see a lot of people answering heavy-duty road transport, also stationary energy storage, rail. So that's good for us because our projects are working in these, are targeting these applications. So that's good. Not so much aerospace. That's not a lot. Aviation also not. But yeah, this gives us a very useful picture of where participants see the strongest potential for future application. And I think that matches quite good what we are working on. So that's encouraging, at least. So stationary energy storage, yeah, is the winner, and heavy-duty road
but
transport.
for stationary energy storage, the volume is not so critical. I mean, if we don't achieve the volumetric specification, it won't be a problem, because stationary storage has not such a big volume limitation. So, well.
I see. That's an interesting point. Yeah, good to know. Yeah. Are there any more comments or ideas from others on this question? We have to cool down. Yeah. Okay. Next question is, what type of support would accelerate the market uptake the most? So this could include funding, industrial partnerships, demonstration sites, testing infrastructure, standardization, certification pathways, policy support, and stakeholder networks or follow-up research. So we are also interested in what do you think is the most critical, what we would need as a support for market uptake. Thanks, Teodoro, for answering in the chat. So to the answer regarding the you have to cool down is that the MOST-H2, the lab scale deliverable hydrogen results are 10.5% and 48.8 gram per liter volumetric. So this is 100% stable up to 240 cycles. Just reading it because I don't know if everyone is looking at the chat. Okay, so here you say that most of you think that public funding is really the most critical support that we would need to accelerate market uptake, but also industrial partnerships and pilot demonstration projects, yes. Some are also saying regulatory support and cross-sectoral collaboration and standardization, and only one for access to testing facilities, yes. Thank you. Yeah, this is also relevant for us when we think about what is needed after the projects are ending, because every project has just a lifetime of 4 years, and then we need to think, or less, then we need to think about what is happening afterwards, because of course we are not yet there to go to the market. So this is very relevant for us also. Maybe also from speaker's side, you have an idea what would be most critical for your specific project. If you want to contribute here, you can, of course. Maybe there's something that you think is often underestimated when discussing the uptake of hydrogen storage. You can just contribute with perspectives.
Yeah, from my perspective is the standardization. I mean, yeah, also regulatory, because we really designed the tank and the test rig without any standard references. So yes, this is quite important to have some references for if you want to commercialize these systems.
Yes, true. Okay, that's a valid point, yeah. Standardization is really often underestimated, yeah. There's another question in the chat. So what hydrogen purity would you get from the dissolved hydrogen? What have been the feedback from the industry so far in MOF-based hydrogen storage? Yeah.
It's probably one of the purest hydrogens that you can have, because everything operates at liquid nitrogen temperature. So nothing else than hydrogen can survive. Maybe you have some traces of helium, I don't know, but it's more pure than the purest hydrogen that you can buy. It's more than 6.0. That means 99.449. It's because everything is treated in liquid nitrogen. So everything is let's say, condensed or solidified in this temperature, everything else.
Thank you for answering that, yes. Hope this answered the question. Then we also have another one in the chat. So
sorry. Wait here. I wrote the question.
Yes,
just the second question would be interesting to understand. So, if you have any feedback so far from the industry, is there any feedback, or you haven't approached the industry so far?
In our case, not. We are just concluding the project actually, so it's too early in our case for industry, let's say. What we have seen is that, as I said in my talk, there are certain advantages when trying to use this technology in heavy duty transportation. I also apply here to a comment about hydrogen cars. Also, I think there's no chance for a car. The system will be way too bulky because it needs some. It doesn't need on-site cooling, let's say, but at least it needs, heavy insulation. So this makes it bulky. The technology goes for mobility, yes, but for large scale, heavy duty, road transport, maritime applications, and maybe aviation. So that's it. When you increase the size, you also gain in terms of batteries, because you would need very huge batteries. But also you gain from the compression needed for huge systems to compress extremely large quantities of hydrogen, or liquefy extremely high quantities of hydrogen. So this is the sweet spot in my mind for our application. You need something bulky.
Okay, thank you.
Thank you for the question and also the answer. So yeah, we had another one in the chat. I think that was Richard Blom. How big in volume will a hydrogen storage system be that have a size of 500 kilometers, including the liquid hydrogen cooling system, compared with gasoline and electric cars?
Yeah, it's more or less the answer I gave, and Teresa also wrote.
Yeah.
Okay, so that is already answered, yes. Sorry, I'm sometimes lost in the chat, but yes, thank you for that. Then I think we can go to the next question in Mentimeter, yes. So next question would be, what is the single most important action needed to move adsorption-based hydrogen storage closer to market? So if you had to choose only one action, what should happen next? This could be, for example, a technical action such as a demonstration or validation, or could also be a strategic action such as stronger, for example, industry involvement, or targeted funding, as we already said, standardization. So whatever comes to your mind. Prove it works, yes. 3 exclamation marks. Give you a bit of time to think about that. It's one of the most interesting questions, I think, also. Political commitment. Advertise the benefits, of course, yes. The impact, show the impact. Maybe if you want, you can also speak up if you have more context here. A new hydrogen hype wave, yes, that would be nice. Or also from the speaker side, maybe you have also one thing that for your project would be the best to happen next. concrete action?
I would guess, and I don't know if the colleagues from MAST3RBOOST agree. We are in let's say in a TRL, in a low TRL level. It's 5. We just, let's say, will test in relevant conditions. So in my mind, we need another period, let's say another 5 years at least, and another funding scheme to take the results from these 1, 2, 3, 4 sister projects, whatever there is out there, and consolidate everything to an attempt to make it go to a higher TRL level. This is a general problem with the European projects. You start, you build something, you reach a certain TRL level, and then something else is funded, and things are forgotten. So, in my opinion, the most critical thing at this point is further funding for 1 or 2 projects that can take this TRL 5 to TRL 7, let's say, and connect it with industry.
Yes.
I don't know, Teresa, Paulo, perhaps you feel it's more ready. I don't know your opinion on this.
Yeah, I agree with you. And also, well, many of the comments are in that line. I guess that political commitment and will also try to mean economical and research commitment, I guess. Yeah.
Yes, definitely. No, I also feel like that.
I also guess, I think that if we start putting hydrogen move cars of one of other hydrogen storage in the roads, it will be easier to move to a adsorption-based hydrogen storage system. But we have to convince people that this technology is also good for traveling.
Yep, I mean, at least now we have the materials. There are 3 or 4 projects that have been working with materials for hydrogen storage, porous materials for hydrogen storage. So obviously we have a good palette of materials at this moment, which we didn't have 5 years ago. So that's the advantage for the moment.
Yeah, that's it. So we can keep optimistic in any case, but it will take more time. That's true.
More effort as well, technical, scientific, and economic.
Yeah. Okay. So I think we have more or less covered all the responses here as well. There's another question by Richard. Is the best MOF material similar to a zeolite in prose? I'm not sure how to pronounce it. Can you answer that, Theodore?
I don't understand the final word.
Question. The price, I'm sorry. Price.
Yes. Price, okay.
That was a typing error. I was also
yeah. No. It's more expensive, but let's say the calculation, it's much more expensive, the MOF, this case, but the calculations or the estimations about scaling up put some of the MOFs, not the very special ones, in the area of expensive zeolites, like 13X, for instance. So let's say the estimation is around the same price as for the future, of course, is around the price of zeolite 13X, which is $20 per kilo, something like that, 20 euro per kilo. But this is on a large scale production estimation, right? For the moment, 10 kilos is nothing. I mean, Again, if the MOFs are based on strange linkers or very expensive metals, this will never happen. So it has to be something.
Yeah, that's the good idea of our colleagues of South Africa. That I think they were at the meeting, so they can join in the discussion. But our MOFs are made from PET in the case of the organic linker, and from other industrial residues. So the heating and synthesis procedure will be almost as expensive or as cheap as the general process for other MOFs, but the precursor is a good approach not only for the price, but also for the sustainability of the process. We should look for use of residues and to avoid the exploitation of mines or resources that can be used for other things.
Okay, can I just ask a voice question because it's too much to write? Adsorption-based hydrogen storage, one of the major issues, certainly the cooling, is one big issue that you really have to cool it down and keep it kept. If you leave your truck then on the airport for 40 days in the sun, I mean it will probably not be very good. But another thing is that you actually have problems getting out the last part of the hydrogen, because you might, have to stop at 2, 3, 4 atmospheres of pressure, because the system will need a certain pressure, and everything below that. And if you look at the isotherm, it's quite a lot left in the tank at that point. Do you have any strategies to get out that part? Do you need to heat it up, to room temperature, or how is that?
Yes.
Yes,
maybe,
Theodore, please. You.
Yeah, sorry. This is exactly why there is a sweet spot in the application window. Let's say you need to choose applications where you don't leave, for instance, your car for vacation 15 days in the airport. No, you cannot not do this. It has to be used in a regular daily basis. So this is for trucks, for professional staff, trains, maritime, because always you need energy and so on. And as for the let's say for the amount that stays inside, so in our case we consider 5 bar as the lower pressure. This is usually let's say the gold standard is 160K 5 bar. So in practice, you cycle your material between 80K, let's say liquid nitrogen temperature, and 160K. This can be made passively or by clever means, by destroying the vacuum around the insulation, or even by heating. But anyway, the design of the material here comes into play. What you need actually is pores that are practically above 1 nanometer. So when you have very small pores, ultra micropores, or even pores in the area of 8 angstrom, 0.8 nanometers, there is a lot of residual hydrogen even at 5 bar at 77K. So what you need is to increase your pore size and make sure that your material is easily desorbed under 5 bar, even at 77K. So it goes with the shape of the isotherm. If you have a very sudden increase at low pressures in your hydrogen isotherms, then a lot of material will stay inside, and you lose significantly in what we call deliverable capacity. When on the other hand,
is the kind of S-shaped isotherm?
No.
No?
You can have a shaped isotherm, but these are new classes of materials. You need to have some flexible stuff for these. in typical porous materials like the MOF we studied and like the activated carbons and so on, what you need is to avoid very small pores because they trap hydrogen very efficiently, and this means that they cannot release it. So you have a lot of hydrogen inside, but you can deliver small quantities because most of it stays inside. So you need a bit larger pores, but not that large so that you add empty space in your system. So this is the interplay between, let's say, volumetric and gravimetric capacity, and this is why you need balanced performance. So what you mentioned about the S-shaped isotherms, that would be the ideal way. If we can imagine a material that can absorb no hydrogen up to 5 bar, and then at 6-7 bar, suddenly the uptake increases, then that would be the ideal scenario.
I mean, you have that kind of isotherm for water, for instance, in some of these aluminum MOFs.
Yes, you need
which are quite nice.
Some flexibility. So you need your adsorption to be able to change something in the structure, open a gate, or change the pore volume of the material. But this so far they are not, used for hydrogen. I mean, nothing that has enough capacity has appeared in the literature. It works for water for sure. So this is the trick they use for water capture from the air. It may work for CO2, not yet for hydrogen.
Okay, thanks.
Thank you for that.
I put again the reference of the work we have just published a couple of weeks ago about the hydrogen storage capacity of activated carbons, and we are working on the same condition as Theodore said, between 100 bar and 5 bar, and we have a hydrogen storage amount of 9.8% weight percent and a working capacity of 9.7% weight percent. So we are almost keeping the whole capacity of the material in that condition. We help the discharge with small heating. That's true, but well, it's not.
Thank you. Yeah, thank you for providing that. That may help also to get a bit more into detail. Yeah. Okay, I think we have one last question, if I'm not mistaken. Yes, how confident are you that adsorption-based hydrogen storage will become a viable solution within the next years? So this is the final Mentimeter question. We just would like to ask for your overall assessment after the whole discussion now and the presentations. Just what do you think? Are you not confident at all, or are you moderately confident or very confident maybe also? See, this is just as a final assessment to see where we stand maybe also in this round. Okay, that's encouraging. Then most people are confident. Let's see. I give a bit more time. I think people are still thinking, yeah, slightly confident is a bit more strong now. So it goes down. Let's see. I wait. We can still wait a bit. Have a bit more time. Okay, 50% more or less responded. And the winner is slightly confident. But I guess this is very well reflecting also what we discussed until now. It may take several years still until we can really talk about this as a market-ready solution. But we are working on it, and we do our best to get there. Okay. So as time goes by, I think we need to move on. But thank you very much, everyone, for participating to the Mentimeter and also for the lively discussion. That was very nice. So I think we have collected several valuable perspectives already, but we still have one point on our agenda, and this is the consolidation part, where we return to the key results presented by both projects and also reflect together on common challenges, future research needs, and possible next steps for the uptake. So maybe, Sibalis, if you want, you can go back to the project presentations, because I think now it would be nice still to hear from both project point of views, but also, of course, the audience, if you still want to contribute regarding, more project-specific questions. So I would suggest maybe that we move this discussion around the common challenges you see across MOST-H2, MOST-Boost. I mean, you already mentioned some, but I think now after the discussion, we can still go back maybe also which future research or development needs should be addressed more concretely. Maybe you have more specific ideas, and also what would be the most useful next steps. So try to be as concrete as you can, because this would help us also to see what we could do afterwards. So I give the floor back to the speakers, and I think you can have 10 more minutes until we end the session here. And the audience is, of course, invited to still contribute in between if you want. So maybe to start with the common challenges, I don't know if this helps, if we structure this a bit around these questions. There's still something going on in the chat in between. We are on all channels here. Yeah, so maybe we can start with this question. Yeah, what do you see as a biggest challenge between MOST-H2 and MAST3RBOOST still?
In principle, I think it's possible to use composite materials for the storage. We have to take to consider that here we are at low pressure, because we are 100 bar. That is quite low if you compare to a pressurized tank that may reach 800. So where composite are where composite play a role. So here we don't have this kind of stress, but we have together we have low temperature. So it's the combination of low temperature and pressure that may guide the utilization of materials.
Teresa, Theodoro, you want to comment on that? Or
on the challenges, first a little bit about the thermal effects. Indeed, the cooling and thermal management in general is extremely important. In my opinion, it is important only in the charging period, let's say, because the period of use is slow and the effects are masked, by time. On the charging, though, you have to charge your tank very quickly, and then you have large temperature variations. You have to quickly dissipate all the heat of absorption, and so on. So thermal management is of course, a big issue. And process design plus the materials used, plus future materials like the composites that can be used may prove advantageous. It is a problem, not the major one. And this takes me to the challenges. For our case, it's probably the price of the material that is decisive. I can disclose the information that our MOF is based on zirconium. Not an extremely, costly material, but it's not extremely cheap. Then you need some linkers to make your material efficient. These are all costly, so it has to do with upscaling plus cost. So how much can you reduce the price if you go to larger scale production? And this is coupling with the upscaling science also, because the chemistry changes. It's not the chemistry that you use in the lab the same that you use in the industry. So new production routes should be discovered in order to reduce the cost. Now, if you have a porous material that is the cost can compensate, let's say, the waste of energy in compressing or liquefying and so on, and also the cost of the tank for the traditional cases, then you have a solution that is viable. Okay. It's also the safety issue, because our systems are much safer in terms of both temperature, pressure, and so on. But my experience says that the industrial motivation is cost. So if you can find a material that is stable enough to cycle it thousands of times, and then the cost per kilo is comparable, let's say, to a normal zeolite, for instance, then we have a case. So cost is the challenge to conclude.
That's one of the biggest ones. Yes, thank you very much for that. Yeah, I think you already answered also the second angle I wanted to look at, which future research development needs should be addressed next. So I think that was already covered more or less also. Yeah, we need time, we need more, we need funding, of course, we need also the industry to play with us, so to go in the same direction, so that we can go further. Maybe as a last guiding question, what would be the most useful from your point of view next step towards uptake after the current project phase? So the next one, I mean, we already talked about it a bit before, but now after also the discussion with the audience, would it be another project so that we have more time? Would it be more research oriented, more specific results that we should target? What do you think? Is it maybe a combination of everything? Probably. So maybe, yeah, everyone, you can still comment on that political commitment I see in the chat. I think it's a combination. But yeah, maybe you can still react to that, and then we can come slowly to the close.
Just a short comment on this comment about the use of hydrogen versus fossil fuels, for instance.
Ah, yes.
I mean, as I said many times, people are not idiots. You know, they use diesel for a certain reason, because it's easy, because it's cheap, because it has everybody has experience, it's handleable, so on. It will always be cheaper, and hydrogen will never be cheaper than diesel. The point is that diesel, like poisoned food, you know, with poisoned food is from, okay, you can buy it cheap, but it poisons you. So there's a turning point when we discover that using fossil fuels cannot be afforded anymore by humanity. Okay. And hydrogen will always be based on this turning point. It will never be as cheap as the fossil fuels, at least not in our lifespan, let's say. Diesel will always be, or oil will always be cheaper. But it's killing us slowly, or less slowly as time goes by. So at some point it will become essential, let's say, to change the point of view. Yeah.
So we need fair pricing of CO2 emissions. That would be one comment in the chat.
It's a big conversation.
So,
it's a big
topic. Yeah, we could do another seminar about that.
Yes.
A whole seminar with politicians and different industry representatives. Yeah. Is there anyone else who wants to comment on these questions, or has another idea, another thing that he wants to share with us? he or she, of course. Because if not, now it's 2:30 p.m. and officially we are done. So I will do our last speech before we close. So thank you very much, everyone, for being with us today before the summer break. We really appreciate that, because it's really not the normal time of having all of these webinars and workshops. So thanks for that. Also for your active participation, that was really, really great. We really appreciate that as well. Actually, so it's recorded. You will find the recording on our website soon. Please follow the projects if you're still interested. I mean, the project is still running, and afterwards we will, of course, try to see how to further move this important topic of hydrogen storage. The recording will be made available on our websites and also on our YouTube channels, so you can have a look there. Special thanks again, of course, to our speakers. Thank you for taking the time, for presenting the project, also for putting you out there to the questions of the audience. I know it's not always so easy, but thanks for that. And we really appreciate your work here as well. And yeah, all of good luck to you as well after the project, that this goes on in the positive direction. We will try to see how to support you here and how we can work together. And yes, we will also provide everyone here with a short summary. So we will try to put everything together, what we discussed here. Maybe this can also be helpful for the post-project continuation. Maybe we can put it into a small policy brief. So maybe, who knows, this might be helpful. It's always good to have a feedback from the audience. And yes, just from general information, I know that MAST3RBOOST has another webinar or workshop next week. So I don't know, Estebalis, if you want, you can still maybe put the link here if there's anyone interested, or if you want to comment on that.
I will. We have another workshop on Tuesday, 21st, about hydrogen opportunities in the funding sector. I will share the link here so you can register and attend to this new webinar. As I said, next week. It's going to be interesting with another project. It's called IHMIE. So I will leave the whole comments here on the chat, okay? So you can register.
Perfect. Thanks for that. So yeah, everyone interested is highly invited to also join MAST3RBOOST's next webinar. For MOST-H2 side, we will now focus on our final event, which is still to be finally planned. It's in September, so we will see if we can integrate anything stakeholders' perspectives there, maybe online. We will still see. So nothing's set in stone, but of course we will let you know when we plan something, and we would be really happy if you would like to join here as well and give us your perspectives there. We will be a bit more advanced still at the very end of the project. And with this, I think we are done. If there are any more questions, comments now, you still have the chance now one last time. Otherwise, I would like to say goodbye and wish you a good afternoon. Here are the chat informations from Estebalis. It's now here. Good. Then I think we can close the meeting. Thank you very much, everyone. Have a nice afternoon, nice holidays. Maybe see you after the summer break again.
Thank you.
Thank you.
Bye, everyone.
Thank you. Bye.